Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from definite integrals, right? So here we have this problem, that is we have to find the integral from 0 to infinity x square over a square plus x square raised to 5 over 2, right? So here in order to solve this problem we'll make use of the method of substitution, right? So let us first call this integral as I, and here what we will do, will substitute x is equal to a tan theta, right? So here a is some constant, and here we are making this substitution, x is equal to a tan theta, because once we substitute x is equal to a tan theta in a square plus x square, we can apply this identity, that is 1 plus tan square theta is equal to secant square theta, right? So now I becomes c x is equal to a tan theta. So what we will do, we'll differentiate both sides with respect to theta. So we have dx over d theta is equal to a secant square theta, right? So dx can be written as a times secant square theta d theta, right? So for dx we have this value, and now see here x varies from 0 to infinity, right? So since we are changing the variable from x to theta, so let us change the limits accordingly. So when x is equal to 0, see a tan theta is equal to 0, right? Since a is a non-zero constant here, so tan theta is equal to 0 and theta is equal to 0, right? So when x is equal to 0, theta is equal to 0, right? So now when x is equal to infinity, then a tan theta is equal to infinity, right? So here we'll take x is equal to infinity. So tan theta is equal to infinity, and we know that for theta is equal to pi over 2, tan pi by 2 is infinity, right? Okay, so here tan theta is not defined for theta is equal to pi by 2, right? So now our original integral, it takes the form, and that is from 0 to pi by 2, right? And for x we can take a tan theta. So here we have a square tan square theta, and in the denominator we have a square plus a square tan square theta, and this is raised to 5 over 2, and for dx we can write a secant square theta d theta, right? Okay, so now we can simplify this expression and see here a square and a, when we multiply these two terms, a square and a, will get a cube. We can take it outside the integral, so we have 0 to pi by 2, and in the numerator we can have tan square theta secant square theta d theta, and in the denominator we can take a square common, right? So now we can take a square common in the denominator, so we can separately simplify this expression. See, if we take a square common, we have 1 plus tan square theta and to the power 5 over 2, right? And see, for 1 plus tan square theta we can write secant square theta. So we have a square and secant square theta and raised to 5 over 2. So this 2 and this 2 and this 2 get cancelled. So now we are left with a sec theta raised to 5, right? So we can write a raised to 5 and secant raised to 5 theta. So now we can substitute the value of this expression as this. So we have a raised to 5 and secant raised to 5 theta, right? So now we can cancel out some terms here. So a cube get cancelled, so we are left with here a square, and here secant square get cancelled, so we are left with secant cube theta, right? So we can now write 0 to pi by 2, and we have tan square theta d theta divided by see, here we have a square in the denominator, so we can take it outside the integral, and here we have sec cube theta, right? So now let us write this integral in the form of sine theta and cosine theta, right? So what we will do, we have 1 over a square, here we have 0 to pi by 2, and for tan square theta, we can write sine square theta over cos square theta, right? And here we have secant cube theta in the denominator, so now we can multiply this term by cos cube theta, right? Because secant theta is equal to 1 over cos theta, right? So now we can further simplify this integral. So we have here sine square theta, and here cos square theta, and cos cube theta get cancelled. Here we are left with only cos theta, right? So here we have now cosine theta, right? So now this integral, after making the substitution x is equal to a tan theta, it reduces to this integral, right? So now I can be written as 1 over a square, and we have 0 to pi by 2 and sine square theta cos theta, right? And now we can solve this integral by again making use of the method of substitution, right? Because see, if we take t is equal to sine theta here, then the derivative of sine theta appears in the integral, right? That is dt over d theta is equal to cosine theta, so dt is equal to cos theta d theta, right? And cos theta d theta appears in the integral, right? Okay, so here we are making this substitution, t is equal to sine theta. Now here see, theta varies from 0 to pi by 2, right? So let us change the limits again in terms of t. So see, when theta is 0, then t is equal to sine of 0, that is sine of 0 is 0, and when theta is pi by 2, then t is equal to sine of pi by 2, right? And sine pi by 2 is equal to 1, right? So now this integral I, it takes the form 1 over a square, and now in terms of t, we can write this integral as 0 to 1, and for sine square theta we have t square, and for cos theta d theta we have dt, right? So now we have a very simple integral here, and see, we know that the integral of x raised to n dx is x raised to n plus 1 over n plus 1, provided n is not equal to minus 1, right? So here we have t raised to 2, so I is 1 over a square, and the integral of t square, here n is equal to 2, so we have 2 plus 1 3 divided by 3, and the limits are from 0 to 1, right? So now we can take this 3 outside, so we have 3a square here, and we have t cube, and the limits are from 0 to 1, so we can now substitute the limits. So we have 1 cube minus 0 cube, and see, this is 1, this is 0, so 1 minus 0 is 1, so we are left with 1 over 3a square times 1, so I is equal to 1 over 3a square, right? So viewers, the value of this integral is equal to 1 over 3 times a square, where a is some non-zero constant.